Shapes and sizes, comparing areas and volumes. What happens here is you get a question and you're asked to say, would this size be bigger than this, or how many of these would fit in this, etc. So the notes here on this section are, it's often appropriate to compare different shapes and volumes, or to convert one shape or volume into another. Comparing shapes allows us to establish which is larger, or whether they're equivalent. For example, whether a round pizza of a given radius is larger than a square pizza with a different length. Establishing the volume of a given shape, we can determine how it compares with the volumes of different shapes, other different shapes. For example, how many glasses of a particular size can you fill from a particular bottle or jug? So this is what's going to happen in this section. We're going to move various volumes around and we're going to compare them. And we've got composite areas or composite constructions here, or composite shapes or vessels. So we'll start off here with a composite shape consists of a square of length 5, this is it here, and a semicircle with diameter 5 units on one of its edges as shown. What numbers of circles of radius 1 unit would have the same overall area? So what we have here is we've got this shape and a small little one of these. And how many of those would fit in there? If you were to completely rearrange the space, not that they wouldn't have to worry about fitting the edges or anything like that. How many will fit in there? Which is equivalent? Okay? So really what we've got to figure out is what is the area of that space there? And what is the area of this? And divide one into the other. It's as straightforward as that. Is that okay? So we start by saying, well, this is the composite shape. And if it is it made up of two different shapes? This one here is, what do we call that one? A square. It's at least a rectangle, but it says 5 by 5, so it's a square. And this one here? Semicircle. Okay? And both of those are in play at the moment. The square is 5. So the area of a square, if you look up the formula, but you really probably won't, the formula is just the length by itself. Is that okay? So for the given square of A, it's 5 by 5, which is 25. And again, you would probably have units here. It might be centimeters squared or whatever. Okay? What's the area of a circle? A is equal to pi r squared. Do we have an equation for the area of a semicircle? Is it in? We do. I mean, I don't know whether it's in the tables, but let's assume that it's half. Is that okay? So we now know that that's for the circle, so it must be half that really. Okay? Pi r squared. That would be the area of a circle. What's the radius of this circle? That's very important. You can easily be confused. You're thinking 5, you're thinking diameter and all of that. But actually, the r is actually only, there's 2 r's in that. That's the circle. Is that okay? That's an r. So the r is 2.5. Isn't that right? Because there's 2.5 to here and 2.5 to here. So our radius in this question is 2.5. 5 over 2 is 2.5. That's the area of a semicircle is pi r squared over 2. And the area is 2.5, so it's pi 2.5 squared over 2, which when we calculate out, 2.5 by 2.5 is 6.25, and that the pi is there, divide, etc. And we get this answer here. So this is the contribution to the area from the semicircle, and the contribution from the square is 25. What's the overall area? What do we do? Just add the two together, isn't it? So the overall area is the composite area, and we say this is the total area is the area of the square plus the area of the semicircle. This can be expressed as the 25 plus the other. Now, circles of radius 1. What's the area of a circle of radius 1? What's the area of a circle? What's the formula for it? A is equal to pi r squared. But we'll call this R1 and this R2 or something like that. Or that's R1 and R1 and that's R2. Okay? Or R for the semicircle and R for the circle. What's the R here in this case? 1, because you're told the radius is 1. So that A is equal to pi. Anytime I see an R, I put in 1 squared. A is pi. Is that okay? That's the area of the circle. So what we have now is, we've got the overall area TA of that shape turned out to be this, but the area of the circle, AC maybe, was just pi. How many of those go into that? How do we do that? Just divide. So we say the number of circles of radius 1, which would have the same overall area, is 1 divided by the other. So we just take the top line, divide by the bottom line. That's a calculator, pi, all that. Can we do all that together? And we get an answer. 11.08 of them fit there. Is that okay? We'll now move on to the next question here, example 2. And this is a bit more substantial. It might look tricky on first read, but after what you've covered, it should be okay. Example 2. A cylinder of radius 5 centimeters. Here's our cylinder, and it has a radius of 5 centimeters. Contains water up to a height of 8 centimeters. So the water is up to the higher level there. 2 identical cones of base radius 2, these are the small cones here, and slope length 4 lie at the bottom of the cylinder. Slope length now, that's an important observation. Slope length. If the cones, now you can see the cones are at the bottom like junk at the bottom of a tank or something like that. If we take those 2 cones out, just fish them out, what will happen to the level of the water? It'll come down. And we're asked to find out how much will it fall. Okay? Now, it's just Sudoku. We have to figure out how much will the height drop, but it's just step by step by step. As I say, it's like eating an elephant, 1 bite at a time, you know? Now, if the cones were removed, what drop in the water level would occur? Well, there's one thing that's important in these questions, is that the cones, when they come out, how much volume will they free up? The same volume as the amount of water that was there. You can't create volume. So if I take out a cone, whatever volume this had, that we think it's filled with water, is going to be gone. Is that okay? So the volume of these 2 cones will be the same as the volume of the water they're covering up at the moment. Is that okay? So if we just stick with those 2 things being the same. Okay. Now there's a few steps in this. We'll start with the cones. It says that if the cones were, 2 identical cones of radius 2 and slope length, that's important, 4 centimeters. Now, what happens here is that if we look at an enlargement of the cone for the moment, it says that the radius is 2, but the slope length is 4. Normally, the equation you're given is h, the height of the cone. And the height is this letter here, which is always the vertical height with the right angle on the bottom. Is that okay? But we were told the slope here. So effectively, we've been told that this is 2, that's h, and that's 4. But that's a right angle. Anything come to mind? Pythagoras. That's a right angle. 2 something and something. We know that x squared, y squared, z squared. The square of those will work. Now I'm talking about the triangle. I'm talking about the right angle triangle like that. Is that okay? We know that's a right angle triangle. And if it is, Pythagoras applies. 2h4. So we can work that out. We can say 2 squared plus h squared is 4 squared. What's 2 squared? 4. H squared we leave. What's 4 squared? 16. How can I get rid of this 4? Subtract, isn't it? or take it to the other side. So 4 minus 4 plus h squared is 16 minus 4. In other words, taking the 4 to the other side, h squared is 12. If I know that h squared is 12, how could I find out h? Square root of this gets rid of this. H is equal to the square root of 12. Is it going to be a positive value? It will, because distance is always positive. Is that okay? Always in that sense. So that's going to be a positive value. So it's going to be, it turns out in the calculator to be 3.46. Just the square root of that. So I now know the height. I know the height, the vertical height of the cone. I'm not in a bad spot. H is 3.46 or whatever, 4 or whatever. I don't have to keep a million places of decimal. Let's go back to the question. What was I trying to do? I was trying to find out the volume of the cone, wasn't I? Now, there's an equation for that in the tables, which I've written down, or I would have written down in the question. V is 1 over 3 pi r squared h. Do I know r for this cone? Was I told it was 2 centimeters in radius? So I was told that r was 2. Did I find h? H was equal to 3.46. So what do? Into lockdown, you've got your table, and you say V is equal to, okay, 1 over 3, fine, pi is pi, or, oh, I have a number for that, I substitute the r squared with the 2 squared. And the h was the square root of 12, or 3.46, whatever I want. Is that okay? That's that. Pi is a number, 2 is a number, that's a square, that's a number. They're all numbers. That's just calculator stuff. And that turns out to be, V is that. What else is there? Let's go back to the question. How many cones were there? 2. So I should multiply that answer by 2, shouldn't I? So I multiply the answer by 2 because both cones. Now I know the volume of water or whatever liquid that would be in the shape of the 2 cones. I know the total volume. Is that okay? I know the volume of the 2 cones. What's that going to be equal to when they come out? Isn't it going to be equal to the amount of water they come down by? Yeah. What is that shape of that water thing? That's a cylinder. The water is actually a cylinder. It's like a band, but it's a disc. It's still a cylinder. It's just got a small height in it. Is that okay? But it's still a cylinder, isn't it? And what's the volume of a cylinder? Well, let's look that up. The volume of this, so let's say if the cones were removed, it would result in a drop in the water level within the cylinder. The drop would be equivalent to the same volume of water being removed. The general formula for the volume of a cylinder, and you can look this up, is pi r squared h. That shouldn't surprise us. V is equal to pi r squared. What's pi r squared? The area of a circle times h. How high that circle is, that disk. So that gives us the volume. So that now is the volume of the water. So we have on one side, should those volumes be the same? Yeah. So what we're going to do in this question is we're going to make V1 equal V2. So I'll just get a nice sheet of paper. The first volume was the volume of the cylinder of water. Now the cylinder of water is fine. Do we know how much it's going to fall? No. So we just call that H2 or something like that. Is that okay? Or H for water, H2. So what we find is the volume of a cylinder is given by pi r squared h. Pi r squared h. We have to be a little bit careful. This is the cylinder and that's the cylinder. And that has to equal all of the stuff we had gone to the bother of calculating for the 2 cones. The volume of the cone, the 2 cones, turned out to be 8 over 3 pi times root 12, or 3.46. So effectively what we have is pi r squared c, hc, is equal to 8 over 3 pi 3.46. Now, do we know anything about the radius of the cylinder? We're told it was 5. So that's given to us. So actually this RC thing was 5. So we can mop that up. So we now end up with pi times 25, because that's RC twice. HC is 8 over 3 pi, 3.46. Can we start simplifying this, anybody? Are there pi's on both sides? The 25, could that go to the other side? HC is equal to 8 over 3, 3.46 over 25. What's HC? The drop in height. Is that okay? So step by step by step by step. H was just, I was trying to call it the height. It's the height in the cylinder, rather than the height in the cone. They're both say, great. I should have called it H1 and H2. My answer would be just that, yeah. That's the answer, it's done. Is that okay? We found the first height, I think we called it, I should have called it CY or something like that for cylinder, and the other CO for cone. The other height, I think, turned out to be whatever it was. We found it on the square root of 12. Is that okay? That's how we did that. So equating the volumes on both sides, the water with the cones, simplifying it, we got the H was that. Using a calculator then, we plugged them all in, and therefore if the two cones were removed, we know how much the water would drop. Now, this is the last question, I think, in this subsection. Very, very similar to the other one in terms of difficulty. One tiny additional complexity. A company wishes to make candles from a cube of wax 50 centimeters in length. The candles comprise two parts. Each candle consists of a cylinder and of radius 2 to a height of 20 centimeters, topped with a cone on the top. So I've drawn a picture of the candle in a way, and I've imagined it like a cylinder with a cone on the top. And they're small. And what I'm trying to do is, how many of those can you make out of that? Is it a volume comparison? The volume. Now there's one additional thing. Calculate the number of candles which can be made from the block if 3% of the wax is lost in the conversion process. So the first thing we've got to do is figure out how much wax is in this stuff here. Is that okay? So what's the formula for a cube? It's probably length by width by height or something like that, is it? So let's look at that and see where we go with that. We'll come back to that one. Here we'll take this part. Is this a compound shape? Part A and part B, is there? Part A is a cylinder, part B is a cone. So we turn now and we see the volume of each candle can be obtained by the cylinder section and the conic section. What do we know about the cylinder? We were told that it was 2 centimeters for the radius, and we were told that the height was 20. Have we got a formula for the cylinder? Yeah. It's pi r squared for the area part of the circle by the height then to give us the volume part. Is that okay? So V is pi r squared h, but we were told that r is 2. And we were told that h was actually 20. So we just one by one say the pi is pi, the r we substitute in for the 2 squared, and the h we substitute in for the 20. 4 pi times 20, 80 pi. Now the conic section. The conic section we're told is 2 here, 2 across. I think we were told it was 2 across, was it? And we were told that it's got a height of, we were told its height as well of 2. So the conic section is 1 over 3 pi r squared h. That's our standard formula for that. But we are told here that r in this case was again 2 and that h was 2. So we substitute in 1 over 3 pi, or goes in there, h goes in there. And we find 8 over 3 pi. Now, what's the overall volume of that? The volume of the A and the volume of the B. Add the two together. So we get the two together then, and we say the overall volume of each candle turned out to be 80 pi for the cylinder, 8 over 3 for the cone. Add them up together and you get that. Now let's look at the wax in the other shape, if we have it here. What do we have here for the cube? 50 by 50 by 50. V is just really L cubed or something like that. Is that okay? Or in this case, V is 50 cubed. And 50 cubed here is 125,000. I'm going to turn that stuff, 125,000, into these. But I have one thing to do first. What am I to do? Get rid of 3% of it. Now, there's a few ways of doing that, and they're covered in other topics. But 125 by 3%, 3 over 100, tells me that I've this much lost. So I take that out of it, and I end up with that. Or you could have said 125,000 by 97%. And that would have given you the same answer. Is that okay? So we now know how much is available. And how much is each one going to cost us? 82.666 pi. Is that all right? How do I find out how many? Divide. One divided by the other, I end up with 467.84 candles. So what integer value should I use for the candles? 4.67, 467 or 468? You might be thinking of 468 because rounding is normally rounded to the nearest number. But in this particular question, that candle is going to look small. So you have to chuck it. So in that situation, you're actually truncating. Anything that's less than 1, get rid of it. It's no good. So that's why we actually rounded down to 467. And that's the end of that subtopic. Okay?